Good morning, everyone. Welcome to today's presentation. I'm excited to share with you an overview of round-robin scheduling in operating systems. My name is Subhasree Maity, and I am an assistant professor in the Department of Computer Science and Engineering at Swami Vivekananda Institute of Science and Technology. In this session, we'll explore the fundamentals of round-robin scheduling, how it works, and its significance in managing processes efficiently. So, let's dive in and understand this important topic together. Let's delve into the concept of round-robin scheduling. This is a preemptive CPU scheduling algorithm, which means it can interrupt processes to allocate CPU time fairly among all tasks. The core idea is that each process is given a fixed time slice, often called a quantum. When a process's allotted quantum expires, the scheduler switches to the next process in the ready queue. This cycle continues, giving each process a turn to use the CPU. The beauty of this approach is that it ensures fairness. Every process gets an equal share of CPU time, preventing any single process from monopolizing resources. Connecting this to our overall theme, round-robin is a practical way to balance responsiveness and fairness in multitasking environments. Let's walk through the working process of round-robin scheduling. First, all ready processes are maintained in a circular queue, which is key to ensuring fairness and equal opportunity for each process. The CPU then picks the first process from this queue and executes it for a fixed amount of time called a time quantum. Now, if this process finishes before the quantum expires, the CPU simply moves on to the next process in the queue. However, if the process isn't finished, it gets preempted. That is, temporarily halted, and then added back to the end of the queue. This cycle repeats continuously until all processes are completed. The most important aspect here is how this cycle promotes fairness and responsiveness, making round-robin ideal for time-sharing systems. It's a simple, yet effective way to manage multiple processes efficiently while ensuring no process is left waiting too long. Let's walk through an example of round-robin scheduling with 3 processes. We have Process 1, Process 2, and Process 3, with burst times of 10, 5, and 8 units respectively. We're assuming a time quantum of 2 units, which means each process gets a maximum of 2 units of CPU time per turn before moving to the next process. Starting with Process 1, it executes for 2 units, leaving it with 8 units remaining. Then, Process 2 runs for 2 units, reducing its remaining time to 3. Next, Process 3 executes for 2 units with 6 units left. We continue this cycle. Process 1 runs again for 2 units, now with 6 remaining, Process 2 for 2 units, leaving 1, and Process 3 for 2 units, reducing to 4. We keep repeating this process, cycling through the processes, each getting up to 2 units, until all processes have completed their execution. This approach ensures fair CPU time distribution among processes, especially in a time-sharing environment. The Gantt chart visually shows the sequence in which processes are scheduled: P1, P2, P3, then back to P1, P2, P3, and so on until all processes finish. This example highlights how round-robin scheduling operates in practice, emphasizing its fairness and responsiveness. Now, let's take a look at this example of performance metrics. We've assumed the same data as in our previous example, and the time quantum is set to 2 units. First, we need to understand how we calculate turnaround time, or TAT. It's simply the completion time minus the arrival time. This tells us how long a process spends in the system from start to finish. Next, we have waiting time, or WT, which is the turnaround time minus the burst time. This measures how much time a process spends waiting in the ready queue before it gets executed. Looking at the calculated values, Process 1 has a TAT of 24 and a WT of 14. Process 2's TAT is 10 with a WT of 5. And Process 3 has a TAT of 22 and a WT of 14. Now, to get a sense of overall performance, we calculate the average waiting time, which is the sum of all WT values divided by 3. That comes out to 11. Similarly, the average turnaround time is the sum of all TATs divided by 3, which is approximately 18.67. These metrics are crucial because they help us evaluate how efficiently our scheduling algorithm is performing. The lower the average waiting and turnaround times, the better. So, by analyzing these numbers, we can see the impact of our scheduling choices and aim to optimize them for better system performance. Let's take a look at the advantages and disadvantages of this scheduling method. Starting with the advantages, one of the key benefits is that it ensures fairness among all processes. This means every process gets a chance to be executed, which is crucial in maintaining a balanced system. It's also quite simple and easy to implement, making it practical for many real-world applications. Additionally, this approach is ideal for time-sharing systems, where sharing CPU time efficiently among multiple users is essential. Now, on to the disadvantages. One major challenge is the high overhead caused by context switching. Every time the scheduler switches from one process to another, some time is spent saving and loading process states, which can impact overall performance. The performance of this method highly depends on the size of the quantum. That's the time slice allocated to each process. If the quantum is too small or too large, it can either cause excessive switching or poor responsiveness. Lastly, longer processes may experience higher waiting times, which can lead to inefficiencies, especially when dealing with processes of varying lengths. Understanding these pros and cons helps us see how this scheduling method fits within different system requirements and constraints. Applications of round-robin scheduling are quite widespread. You'll find it is widely used in time-sharing and multitasking operating systems, where multiple processes need to share CPU time efficiently. It's particularly suitable for interactive systems where processes generally have equal priority, ensuring that no single process dominates the CPU. You'll notice that popular operating systems like Linux and Windows employ round-robin for process scheduling, which helps manage numerous processes smoothly. One of the key strengths of this approach is that it guarantees fairness in CPU time allocation, especially in multi-user environments, so all users and processes get their fair share. Overall, this makes round-robin a practical and effective scheduling method for modern multitasking systems.